and I'm going to show you a workflow for spectral extraction using Specviz2d. We're going to start picking up pretty much exactly where Zvi left off. So please go ahead and run the first two cells since this is loading that entire Mosviz data set. As you've seen before, this commented out code will load this data from box, whereas these lines here will load the data that is pre-staged on the webinar environment here. So we're just first loading that into Mosviz exactly as Zvi showed. In this case, I'm selecting the first row programmatically from Mosviz without even showing the Mosviz app in the notebook at all. And then extracting the 2D spectrum as we showed as well. I'm then going to load that 2D spectrum into Specviz2d and load it in this sidecar again. Specviz2d consists of two viewers. You have your 2D spectral viewer on the top and your 1D spectral viewer on the bottom. You can either pass separate FITS files for the two viewers if you'd like, or as we did here, we're only passing the 2D spectrum, in which case what you see on this lower viewer here is the default extracted spectrum using the spectral extraction plugin that we'll be showing in a second. One other thing to note is that Specviz2d currently plots first pixels instead of wavelength. We're working on a wavelength calibration plugin coming soon and more capabilities to sync between these two viewers. But right now, that's just why this spectrum might appear kind of horizontally flipped compared to what we were seeing in Mosviz. Also, as we showed, these two viewers have their axes linked. So whether you use a tool in the viewer itself or an API call here where I'm going to set the X and Y limits of this Specviz1d instance, you'll see that both viewers kind of react instantaneously to that change. We've also seen all the plugins in the sidebar here. We're going to be looking at the spectral extraction plugin, but I'm just going to make use of the API here. I think we saw this before for Jesse, but the .plugins attribute here, this is just returning a dictionary of all of the names of the plugins that are available for this instance. So you see those all here, and then the values of those objects are an API access to those individual plugins. So we'll be looking at spectral extraction. We'll just call Specviz2d.plugins, and then this is just accessing the spectral extraction entry from this dictionary, which returns us that API object. If we call dir on it, that's just kind of a handy way, instead of digging into the API docs online, it shows you all the attributes and methods that are available to you on this object itself. On any of those, you could call help, or you could put a question mark after if you're running within IPython or Jupyter. That won't work in just a plain Python instance. And that just gives you the API doc string that you would find online as well. So all of the plugins have this open and tray method and the show method. You already saw those in action. We'll see a lot of these other attributes for this demo here as well. So we'll just programmatically open that in the tray here. So spectral extraction kind of consists of three different steps. The first is defining the trace where the spectrum will actually be extracted. By default, that's just a flat trace, a pixel number. At the end of the demo, I'll also show you some other options. I'll show you how to fit a polynomial to that trace. For the flat trace, your input option is then just the pixel number. So you can see when I change this pixel number, there's a blue line here on the 2D spectrum that's showing where that trace falls. And there's also a blue line in the spectrum viewer at the bottom, which shows you kind of a live preview of the spectrum that would be extracted following all of the steps in this plugin. So what I often like to do for kind of coming up with reproducible notebook workflows is to play with these options interactively in the plugin itself, and then use the API in the notebook to access the value that I set it to. So here 35, right? And then you can build up a little script which sets all of these widgets to the values that you have set interactively so that you can reproduce those same results again. So I already did that just to get the good trace of this object here. Instead, in one line, we're going to change the pixel to 146. We're going to set the background type, which I'll talk about in a minute as well, to two-sided and set its separation. So I'll do that now. And see that updates our spectrum as well. The second step of spectral extraction is defining the background. So you can choose whether you want to extract background from kind of a one-sided window above or below your trace, or a two-sided symmetrically above and below, or you can define another manual trace for the background itself. So here, say you just selected two-sided, we can see when we're mousing over this section, there's kind of a visual representation of where those background regions fall on our image. The separation, again here, just dictates the separation between those individual windows and the trace that we had defined in the previous step, and then the width of each of those background regions. So see again, as I change any of these values, you're seeing the kind of the indication of what that means on the 2D spectrum here, but also a live update of the spectrum that would be created from those options. And then the last section is just defining the extraction itself. There's a few options here. The first is what 2D spectrum should be input into this extraction. From plugin, as it says in the kind of explanatory text below, just means that it's using the background subjected image that was kind of computed on the fly in this section without actually having to export it to its own object. But if you want to do your own background subtraction in the notebook using another tool or whatever and load it into Specviz2d, you could select that entry here as well as the input to the extraction. Or if you want to just forego background subtraction entirely, you could choose the original data and it would just disable your background subtraction. We have two types of extraction. The first is the simple just boxcar extraction. We also have horn extraction or optimal extraction implemented. For boxcar, we can then just set the width of that boxcar window that will be used to create our spectrum. Before we switch to the other data set to show how to fit a polynomial to the trace, I just also want to kind of show this cool example to show the API off a little bit and just how you can use these plugin APIs, not just as a script to reproduce results, but you can use it within kind of more complex Python patterns to do some cool interactive things. So as I mentioned, right, if we go up dir, we see all these attributes and methods that are available for our plugin object. I just told you about this kind of 2D spectrum, what the input data set is for the extraction section of this workflow. That corresponds to this xDataset object in the plugin API. If we print that, we'll see that this API object is essentially just the Python representation of this dropdown, right? It tells you the currently selected value, and it also tells you the valid choices. If you try to set this to something that isn't included in the valid list of options, then it would throw an error and tell you that you can only choose from these two things. So here what I'm going to do is I'm going to set this to Spectrum2D instead. You see that that's reflected immediately in the UI version of the plugin as well. And so we're just skipping background subtraction, right? What I'm going to do next is loop through all of the rows in our 2D spectrum. And each time we go in a new iteration of this for loop, we're going to set the pixel option for the trace, which was the first thing I showed you up here, right? So it's effectively, we're going to be as if we were holding down this button, right? And as we loop through that, because we set the extraction width to a single pixel, and we disable the background subtraction, we're pretty much just going to be looking at what the spectrum looks like at each individual row of the 2D spectrum. So if we run that, you can kind of see in real time as we're slicing through and seeing what the other dimension of that 2D spectrum looks like, essentially. Okay, so next I'm going to load up just this other data set. This comes from ERS program 2039. I'll just kind of drag this over here so that we can see our new instance of Specviz2d. Okay, so this time what we're going to try to do is we're going to instead try to extract the spectrum that kind of corresponds to this really faint signal to noise curve feature that you see here. So again, we'll open our spectral extraction plugin. And this time we are going to choose a polynomial trace. And you'll see that that automatically kind of fails. It's not giving us any results because the pixel, like the combination isn't finding any good fit. We're going to keep the order at 3, but we're going to move our input pixel down. You'll see now that we're actually in the data instead of just the very top pixel. Each time I move this, it's recomputing a best fit polynomial to the data. We'll move this down to pixel 23, right about here. We're then going to tell it to bin in the wavelength direction by 10 bins. And for each of those bins to include 6 pixels worth of width in the data that it sends to fit that polynomial. And you'll see now that our trace decently kind of tracks that really faint spectrum that we were seeing. We could then go down to the background. Here it's defaulting to one-sided, which probably makes sense, but we probably want one-sided on the top instead of the bottom, so we'll provide a positive separation. And we'll have a little bit of room, so we'll increase the width a little bit here as well. Our other option for the background is whether at each of these columns we want to use the average or the median to compute the background flux. We'll choose median here just so that we're not as influenced by any outliers. You'll see that that cleans things up a little bit. What I didn't mention before as well is that we can also export any kind of intermediate steps, right? So if we wanted to see what the background image alone looked like, we could do that here. We'll just call it background and we'll tell it to plot in the viewer. And so this is what under the hood is being computed from this window that defines the background. It then has a single flux value for each of those columns, and it creates this image, which is then subtracted from the original image to get your input for the extraction procedure. You can also get the spectrum that corresponds to that or the background subtracted image itself. So one other handy thing you can do, right? We have all these ability to get the kind of intermediate steps from the UI. But if you do it from the API, it kind of saves you a step of having to save it into the app and then do another API call to extract it. Because all of these methods return the Specutil Spectrum1D objects themselves. So you could just request the background image as a Spectrum1D object without having to actually visualize it. It's particularly useful if you want to do any of your own kind of logic in the notebook and then re-inject a new Spectrum object into the app. And so similarly, I'll just show here for the extraction, I'll now set, widened a little bit to just 2 pixels. And this time, instead of clicking extract in the plugin, I will call export the extracted spectrum in the API. And by passing add data equals true, it just means to inject those results back into the app with this label. So when I do that, you'll see that this updates. We've replaced the default kind of extracted spectrum, which was just guessed from basically finding the brightest pixels in the image, with the one that we have defined in the plugin. And it also gives us that corresponding object in the notebook to do any other sort of saving to a file or other analysis with other tools.